Welcome to the chapter on chemical reaction engineering. This field studies the rates and mechanisms of chemical reactions and the design of reactors where these reactions take place. It is essential for scaling up reactions from the laboratory to industrial production. In this chapter, we will cover reaction kinetics, reactor design, and catalysis. Reaction kinetics is the study of the rates at which chemical processes occur and the factors that affect these rates. Understanding reaction kinetics is crucial for designing reactors and optimizing reaction conditions. The rate of a chemical reaction is defined as the change in concentration of a reactant or product per unit time. For a general reaction where moles of A react with B moles of B to produce C moles of C and D moles of D, the rate can be expressed as follows. R equals -1 over A times the change in concentration of A over time, which is equal to -1 over B times the change in concentration of B over time, which is equal to 1 over C times the change in concentration of C over time, which is equal to 1 over D times the change in concentration of D over time. A rate law expresses the rate of a reaction as a function of the concentration of reactants. For a reaction where A converts to B, the rate law might be R equals K times the concentration of A raised to the power of N. Here, R is the reaction rate, K is the rate constant, the concentration of A is denoted as A, and N is the order of the reaction with respect to A. For a first-order reaction, where N equals 1, the rate law is R equals K times the concentration of A. The integrated form of this rate law is given by the equation. The concentration of A equals the initial concentration of A times E raised to the power of -K times T. Here, A0 is the initial concentration of A. Reactor design involves selecting the appropriate type and size of reactor to achieve the desired conversion and selectivity for a chemical process. The main types of reactors are batch reactors, continuous stirred tank reactors, and plug flow reactors. In a batch reactor, all reactants are loaded into the reactor at the beginning, and the reaction proceeds over time. Batch reactors are often used for small-scale production and for reactions with complex kinetics. A continuous stirred tank reactor, or CSTR, is a reactor in which reactants are continuously fed into the reactor and products are continuously removed. The contents of the reactor are well mixed, and the reaction occurs at a constant concentration. The design equation for a CSTR is V equals the difference between the molar flow rates of A at the inlet and outlet divided by the negative rate of reaction of A. Here, V is the reactor volume. FA0 and FA are the molar flow rates of A at the inlet and outlet, respectively, and RA is the rate of reaction of A. In a plug flow reactor, or PFR, reactants flow through the reactor as a plug with no backmixing. The concentration of reactants changes along the length of the reactor. The design equation for a PFR is V equals the integral from FA0 to FA of DFA divided by the negative rate of reaction of A. Catalysis is the process of increasing the rate of a chemical reaction by adding a substance called a catalyst. Catalysts are not consumed in the reaction and can be used repeatedly. There are two main types of catalysts: homogeneous catalysts, which are in the same phase as the reactants, and heterogeneous catalysts, which are in a different phase than the reactants. For example, acid catalysts in liquid phase reactions are homogeneous, while solid catalysts in gas phase reactions are heterogeneous. Catalysts work by providing an alternative reaction pathway with a lower activation energy. This increases the rate of reaction without changing the equilibrium position. Enzymes are biological catalysts that speed up biochemical reactions. For example, the enzyme catalase catalyzes the decomposition of hydrogen peroxide into water and oxygen. The reaction is given by 2H2O2 decomposes to form 2H2O and O2. The rate of this reaction is significantly increased in the presence of catalase. Chemical reaction engineering is a fundamental field in chemical engineering that involves understanding reaction kinetics, designing reactors, and utilizing catalysts to optimize chemical processes. Mastery of these concepts is essential for the efficient and economical production of chemicals on an industrial scale.